Thanks for watching AI Weekly Update from Henry AI Labs. This is a weekly roundup of the latest news in deep learning and AI, so if you're new to the channel, please consider subscribing and check out the catalog of previous videos on Henry AI Labs focused on deep learning. This is one of the most exciting weeks in deep learning with a really exciting new announcement from OpenAI about multimodal neurons and artificial neural networks. So as shown in this diagram, they're saying that as they're doing these feature activations and feature visualizations where you take an individual neuron and you try to generate an image or do something that will maximally activate that intermediate weight in the neural network, it responds not only to images of a concept, but also to text of the same concept. So you pass it in a Spider-Man image, a rough sketch of Spider-Man, or the text Spider-Man itself, and the same neuron has this abstraction where it responds to all these same concepts in each of these image text modalities. So it's a really exciting advancement, and the same line of work as OpenAI's work on DALL-E and CLIP, and bridging together image and text representation learning. So also on this topic, there's a new data set, an open data set of 38 million image text pairs. So if you are curious about, if multimodal neurons inspires you, DALL-E, CLIP, even like ImageBERT and all this stuff, if it's interesting you to research this, you now have this massive open data set extracted from Wikipedia. So it's always cool to see these data sets come out as well. Next up, Jan LeCun has written a position on self-supervised learning, the dark matter of intelligence. The dark matter of intelligence referring to this idea of common sense and how as babies we learn this predictive model of the world, and we have, we're always predicting the future, and that's how we build our common sense about, plausible predictions of how the future will unfold. So the beginning of this is describing this idea of self-supervised as predictive learning, and then particularly I really enjoyed this section of diving into the difference between how in natural language processing, when you predict the future with something like masked language modeling and left to right, predicting these masked out words, you can do a probability distribution over the entire vocabulary because you only have like 37,000 words, so it's kind of practical to put a probability density on all of the words to continue predicting the future. But in images, it's completely impossible to do that because of how many images there are. Same thing with video data. So there needs to be a different way of predicting the future without assigning probability distributions to these high cardinality amount of outputs. So that's where LeCun ties in these ideas of energy functions, and particularly relating these contrastive learning algorithms like SimClear and SimSciM, MoCo, SWAV, with this idea of joint embedding spaces in Siamese networks. So they're learning a joint embedding space where they predict this energy between the positive pairs. And then he describes further this idea of contrastive energy-based self-supervised learning and how you need to push down on the dissimilar points, push up on the positive points, or I might have that backwards, but you need a way to sample these negatives for pushing down on, and that's a challenging problem. So then LeCun ends it by describing these latent variable models, like the generative adversarial network framework, where you have that latent vector Z, and then you also have that energy-based function in the discriminator, and these kind of strategies for predicting the future when you can have uncertainty in the output. So I thought this is a really great article, and we'll dive deeper into the details of this, and then finally it ends by describing some of the latest research from Facebook, which is SEER. About a year ago, Facebook had used a data set of Instagram images to do weekly supervised learning. This is where you do supervised learning, but the labels themselves haven't been that carefully annotated. In that case, they're using Instagram hashtags as the labels for fitting, for learning on this massive data set. Now what they're doing is they're taking 2 billion Instagram images and they're using the SWAV contrastive learning framework as well as this RegNet-Y architecture. I made a video on how the RegNet architecture came about. It's this paper called Designing Network Design Spaces. So, imagine neural architecture search, but one level higher even, where you're trying to also do AutoML on the parameterization of the search space. So it's kind of a hilarious recursion of this neural architecture search, but it's produced an architecture that's now being debuted in one of these big time papers. So they show this gain over 1% on the using this strategy, and and throughout the weekly update, we'll dive more deeply into exactly how this experiment is set up and the exact results. So next up on the topic of self-supervised learning is self-supervised learning, and it mostly works well when it's in combination with supervised learning and semi-supervised learning. So there are these loops where you have the the self-supervised, the feature extraction, the feature learning on unlabeled data, and then you have it tied into some loop where it's also leveraging supervised learning from the smaller labeled data set. So we've seen a lot of interesting papers in this area like FixMatch, co-match from Salesforce, and now we have this new paper, this new architecture for doing this. And so I didn't get too deep in the details of this, but I do want to just present it quickly because I do think semi-supervised learning is probably where, is probably the most practical way of using these self-supervised learning things in the current state of self-supervised learning. Next up, we have some sobering news about the latest advances in the transformer architecture and natural language processing. So this study from researchers at Google is a large-scale experimentation. It's similar to the text-to-text transfer transformer in that they take apart all these different things that contribute to the end performance. So there have been many ways of trying to build on the original transformer architecture. This first block is, easy replacements, just switching out the activation function and then switching out the normalization layers and the initialization, things like the ReZero paper, then the the depth, the hidden dimensionality of the network, and then these kind of clever things like sharing weights or deconstructing the embedding. So you have different parameterizations for the input embedding table and the output embedding table, and then all these other kind of ideas like the funnel transformer where you pool along the sequence dimension to compress the intermediate dimensionality of the transformer. So when I originally read this paper, I thought it was a comparison with these papers like Transformer XL or Compressive Transformer, or particularly these papers that are trying to attend over a really long sequence of inputs. But this isn't that kind of comparison. This is a comparison with the standard vanilla transformer that does tasks like the glue benchmark, extreme summarization, web questions, and machine translation. But it's not about one of the core motivations for building on these transformers is to have them attend over a longer input sequence. But this is more about, you fix it at, say, 512 tokens, and then you see if these modifications are building upon the performance of that kind of architecture. So this is a really rigorous paper, and I'm excited to share the details of how they set up this experiment and some of their key takeaways. Despite the message of the last paper that these new transformers aren't really performing so much differently than the original one, we still have, since it's another week in deep learning, we have a healthy crop of new transformer architecture. So we'll start with the perceiver, general perception with iterative intention, and this is a really exciting one. The idea is that you start off with this high dimensional input. So say you have a pixel grid, or they even describe point clouds. It could be videos, audio, or it could be text too. You still could use this for natural language processing. So you have you have a high dimensional input array, and you're going to be compressing it into a latent vector and iterating on the attention between these intermediate features of the neural network and the original input data. So it's a new architecture, and it's interesting to see the results of this, and always kind of exciting to see these new designs for neural network models. Transformers are graduating from natural language processing into computer vision problems as well. One of the most famous architectures for doing this is Google's Vision Transformer architecture. The idea of the Vision Transformer is to split this image up into n by n patches and then have a patch embedding for each of these positions, and then you encode them and treat these patches as if they're a sequence of tokens, similar to sequence-to-sequence modeling with the NLP transformers. So this paper, Transformer in Transformer, takes issue with this idea of just blindly aggregating a position embedding for these large patches, because you could say have a 12 by 12 patch with 144 pixels, and they're all aggregated with the same embedding. So the idea is to have an inner block that learns more specific local representations within the patches and then projects it back into the global space. So you have the patch embedding, and then you add in this local embedding that's learned from each of the patches, and that goes back into the model, and then that's your new transformer block for computer vision problems. So we'll dive into this paper and get into how well such a subtle modification improves the performance. The Style GAN2 generative adversarial network framework is produced these amazing photorealistic facial images. And one of the key drivers behind that is the way that they have this mapping network from the latent vector Z into the feature contribution of the latent vector into the upsampling of the generator in StyleGAN. So they have this Z vector that's sampled from a random space, then it gets passed through something like 8 layers of multi-layer perceptron, and then you take that output and you feed it into the upsampling layers in the generator through adaptive instance normalization. And I think they might be even further building on that adaptive instance normalization thing. Have you seen things like the Spade paper from NVIDIA, where say you have like a pixel drawing and then it turns it into a photorealistic landscape? That's done by using spatially adaptive instance normalization, where you have gain and bias parameters for each spatial location of the intermediate features. So that is the idea of StyleGAN, and generative adversarial transformers is building on this idea of having this mapping space from the latent vectors into the contribution of the generator's features by using attention. So you're using these exciting new attention layers to contribute more on the information propagation from these latent vectors into the intermediate features. So it's this idea of this top-down, bottom-up sharing of these attention with this latent vector codes, and we'll get more into the details of this when we are going deeper into it in the weekly update. This week, I also found a really awesome blog post covering the state-of-the-art image generative model. So if you're excited about the generative adversarial transformer, or probably you've been excited about these vector quantized variational autoencoders, and next we're going to look at another paper that's building on this framework. This survey is going to take you through some of the key differences about each of these different recent papers that have come out, and some opinions about where they might be headed and how they differ from each other. So I really enjoyed reading this. It has a lot of great insights about the state-of-the-art in image generative models. If maybe you've been falling asleep on this research, here is something to help you get caught up again with the state of the art. Although this is debuting a bit late in the weekly update preview, this was my favorite paper that I read this week. The title is Ultra Data Efficient GAN Training, Drawing a Lottery Ticket First, Then Training It Toughly. So I have to first just praise the creativity of these authors. I never would have thought that there's a connection between the lottery ticket hypothesis and then data augmentation. So as shown in this quote, the idea is that you have these two subproblems to solve. You first find the lottery ticket, and again, the idea of a lottery ticket is a sparse subnetwork that can be trained from scratch within this dense architecture. And then once you find this lottery ticket, you train this sparse subnetwork with aggressive data and feature augmentation. So data augmentation refers to transformations in the input space, like rotating an image or translating it. And then feature augmentations, I've recently made a video on an ICLR paper titled Modals. That's like a really great example of this. That's where you augment the data directly in the intermediate feature space. So whether you're adding noise to the vectors, or in the paper Modals, they form these class boundaries and do interpolation, extrapolation using the class boundaries in the latent space. But they're using this paper from Google, Adversarial Augmentation. They're going to be using an adversarial controller to control how to augment in the feature space. But I just thought this combination of these two ideas was really interesting, and I'm excited to present further the details of this paper. Back on the excitement of image generative models, we now have a new paper on predicting video with vector quantized variational autoencoders. So amongst the really exciting application of really being able to predict videos at high resolution 256 by 256 with a diverse data set, the Kinetics 600 data set, I really like the way that this paper really explains the vector quantized variational autoencoder well, and describes how you update it with the straight through estimator. And then it describes how the strategy of this algorithm is to compress the frames into the discrete codes from the variational autoencoder, and then you use an autoregressive pixel CNN model to predict into the future directly in the latent space. So it's similar to papers like, it's kind of similar to Mu0, how Mu0 has this tree search that it uses, and it uses its latent space to plan in that tree search space. So you have a compressed latent space that you use to predict the future of high dimensional or high resolution images, so that it saves a lot of computation. So a really exciting approach to compressing the video frames and then using the compressed representation to generate video. Also on the topic of encoding these high dimensional, high resolution images and videos for the sake of learning, improving computational efficiency in visual reinforcement learning via stored embeddings uses this idea of builds on the idea of experience replay. So one common technique in reinforcement learning agents that learn from visual inputs is to save up some of the previously collected experience in an experience buffer that you'll then replay and do more like say Q-learning updates from this replay buffer. So the core insight of this paper is that there's no need to store these high resolution images in the replay buffer. You can compress them into their latent vector codes, and then you can use these latent vector codes for doing the soft actor critic updates. So another interesting, exciting technique for computational efficiency with experience replay in visual reinforcement learning. So next up, I want to present this library on GenoML, AutoML for genomics. And I don't know too much about genomics data, but it seems like it's a cool project. And I just kind of want to show this to you, maybe just to, maybe if someone out there knows more about it and wants to contribute to this. It looks like it's some technique of standardizing the data processing pipelines, obviously the hyperparameter tuning of fitting machine learning models and things like that. But it seems to be an interesting step forward in making this kind of idea of what kind of genetics data is out there, what are the machine learning problems. It seems like this is a really interesting effort on bringing together genomics and deep learning machine learning. Data augmentation for object detection via differentiable neural rendering looks like it could be a step into the future of computer vision. So in computer vision right now, we're usually using these two-dimensional image pixel grids. ImageNet, MoCo, these data sets are usually height by width by RGB pixel grids. But now we're starting to see more and more use of these three-dimensional, image data representations, things like voxels and three-dimensional volumes, or these point clouds, and having these meshes that connect the point clouds, and then this idea of differentiable neural rendering, where you have this camera that you can slide it through a three-dimensional space and then render a two-dimensional projection, by taking like a picture as it slides through the three-dimensional volume. But anyway, so this idea of turning a two-dimensional image into a three-dimensional space and then being able to rotate it by kind of going around the like z-axis is a different kind of data augmentation than what has been explored in computer vision. There's things like two-dimensional rotations and translations, but there's never been this idea of like rotating a camera around the image, around the object of interest, like this wolf, in the z-axis. So I think this is going to be a really exciting idea. Things like the neural radiance fields produce these really amazing images. I think it's going to be really interesting to see how well this works for data augmentation, because obviously, it's adding this new prior. Images are organized in three-dimensional space in the real world. Finally, I'll present some of the key takeaways on this great talk from Chelsea Finn on tackling distribution shift through pessimism, adaptation, and anticipation. So we'll talk about this, how distribution shift occurs in offline reinforcement learning, doing search engine modeling with Google, as well as with language models, and how their performance degrades as the distribution shifts. And then we'll explain these three core paradigms for thinking about this, with pessimism, where you kind of lower bound the data and select the hardest examples. Adaptation, things like model agnostic meta learning, MAML, where you're trying to train a model that can quickly adapt to things. And then anticipation, where you might have a latent variable that can predict the future and anticipate it that way. So we'll go into more details of this, and I'll skip ahead to some of the slides that summarize these ideas. We'll begin the weekly update with the most hyped up, most exciting news this week, which is the multimodal neurons and artificial neural networks released by OpenAI and then also published in the interactive Distill publication. The Distill publication adds on by you can change these things. It's interactive with how you can see the different visualizations of the neurons and play around with this idea. So we'll begin covering this idea by first describing the background of what deep dream is. So the idea of deep dream and the idea of trying to generate an image that maximizes an activation is you take an intermediate feature of a neural network and you treat that like it's the loss function. So the loss function is to maximally activate a intermediate weight or an intermediate feature in one of these neural networks, and you use that loss function to train a generator neural network that might map from, say, random noise Z into the image space, the height by width RGB space, and such that that image is maximally activating the feature. That's where you get the gradient to put it back into the generator's parameters and update it. Or you could just have this iterative thing where it isn't really parametric. It's just you're directly optimizing the image itself without having like some parametric generator that renders the returned image. So that's a more common way of doing it. But the idea of deep dream is to try to visualize what kind of features, what kind of visual features are being encoded in these intermediate neurons by seeing what maximally activates them. The next concept that's important to understand for understanding this multimodal neuron thing is that they're going to be taking apart the CLIP model that they've trained. So CLIP is this model that's learned with contrastive learning between image-text pairs. So you go to the internet and you get these image-text pairs where you have an image of a dog and then it has the caption, Pepper the Aussie pup. And then you would get a whole batch of web images. So say this other thing is, here's me with my new cars, some random text prompt like that, or like this is the largest lake in the US, something like that. And you're trying to make these pairs similar and dissimilar from all the other sampled text prompts and all the other sampled image prompts. So this is the architecture that bridges images and text that they're going to be trying to probe what is activating the neurons that bridge together these text and image domains. So if you're curious about this, here's a Keras code example that implements it uses the MS COCO dataset to implement this idea of having text encodings and vision encodings that get combined together. So in this case, you have the vision encoder, then you have the text encoder, the vision encoder being the pre-trained exception model, the text encoder is the famous BERT model, and then together you have this dual encoder. And the dual encoder is the idea of combining the two modalities and then trying to activate the neurons in this dual encoder that combines the two modalities is what we're going to be looking through in this multimodal neurons and artificial neural networks. So the publication begins by communicating this idea. You begin with this. So first there's this idea of the Halle-Berry neuron, which I wasn't familiar with before this, but apparently in neuroscience they've been able to tell that there's a neuron that responds to this image, photorealistic image of Halle Berry, this sketch, like conceptual drawing of Halle Berry, and then also just the text Halle Berry. So they call this the Halle Berry neuron, and that's what we're trying to look for in this clip architecture. So neuron 244 from the penultimate layer in clip, in the ResNet 50, the 4x width multiplier, this is referring to that last layer that's fusing together the image and the text encodings and then maps it into the final output of the contrastive pair similarity that's also repurposed for image classification with the pattern exploiting training style text prompt. So they're looking through this particular neuron and seeing that it activates with the image of Spider-Man, the sketch concept drawing of Spider-Man, as well as the text of spiders and other things like that. And you can click view more to see other text prompts that activate this neuron. Same thing with the conceptual sketch drawings and the photorealistic images. So it's a really exciting combination. And they show that, you know, previous approaches to like Deep Dream and that kind of thing wouldn't be able to not only just not respond to text, but not even respond to, you know, images and then a conceptual drawing of the same image. So even just this together is a new result that maybe is bridged together with the interface of having text as a part of this model. So then the blog post continues to talk about describe more of these different neurons. So they have region neurons. You see USA, Europe, India, West Africa, person neurons, emotion neurons, shock, crying, happy, sleepy, and other visualizations of, you know, these kinds of things. And it's an interactive blog post, so you can go to face and you can change it to nature and see what Donald Trump, the person neuron, has of this other nature thing. So they talk about decomposing these neurons too to combine new ones. Like they have some example where it's tennis is a combination of two things or something like that. So here's one of the most interesting visualizations presented in the Distill publication about multimodal neurons. In this case, we're looking at the neuron that's been labeled as the mental illness neuron. So this neuron responds to images, concepts, text that corresponds to mental illness. And mental illness describing things like depression, anxiety, and so on. So what this is showing you is showing the deviations from zero activation. So we see the music and sports, something that's completely unrelated, has this far, you know, left tail on this visualization. And then if you put in depression or sad images, like this infographic describing symptoms of depression, it has a serious deviation away from zero activation. And then we see anxiety, bad feeling, depressing jokes. And you see how you can interactively visualize this conceptual multimodal neuron thing and the different activations. Having discovered these neurons that activate to particular concepts, they explore the idea of we can just use these conceptual neurons for classification. So say you want to classify a dog, maybe you can just use these three neurons that are related to different categories of dogs. So I don't know if that would be specific dog breeds in this kind of example, or if it would just generally be dog, wolf, or, you know, even concepts like man's best friend or pets might even be like pets might be some abstract concept that's represented in one of these neurons. So this idea of using abstractions is about taking only 3 neurons in a deep neural network on average to classify ImageNet data. And even with only 3 neurons and having a linear probe on top of those 3 neurons, it still can get a top 5 accuracy of 56%. So that's a pretty exciting result of showing how influential these individual neurons can be on learning these concepts and learning meaningful representations that can map to classification labels. So finally, before concluding with some overall ideas on this multimodal neuron paper, they also show this typographic attack where in order to misclassify this image as an apple, you just write iPod and then tape it to the apple and it misclassifies it as iPod. And this is kind of interesting because it's not really like it's misclassifying it, because it is being trained to do image text similarity, and if something's got iPod written on it, given this data set, that's probably what it was exactly trained to do. It probably has these, you know, as you grab these images from the internet, you probably get like advertising, things like that, like where it would have Apple iPod, and then the text description would be the new Apple iPod released on October or whatever. So I don't think it's like an adversarial attack. I do think it's kind of been trained to do this, but it is showing you this phenomenon of these image text models and the way that they've been trained. So to summarize some of my thoughts on this new research, multimodal neurons in artificial neural networks, OpenAI has had this microscope thing out for a little while now, where they're doing this activation visualization of all these different architectures like, you know, ResNets and AlexNets, and now they have the new CLIP models, which, you know, produce this really exciting research. So overall, I don't know what I think about this, if I'm really convinced that this is going to be something that's, you know, super useful for training deep neural networks. I do think it could be really useful for say the catastrophic forgetting problem or distribution shift, and you're having your model try to adapt to these new data set distributions, and you can maybe now visualize what's happening to these particular conceptual neurons. And I guess that is extremely exciting, this idea of having this interpretability with respect to these neurons. And they do discuss somewhere in the blog post, I don't remember exactly where it was, but they say something like 80% of the neurons are interpretable. Interpretable meaning that when you generate some of these maximally activating images, you can, as a human, look through these images and say, it's clear to me what the concept is that's unifying these images, and then you form a label like the mental illness neuron or something like that. So overall, I definitely think this is a very exciting research, and it's something that I think is pretty new, this really getting something out of these deep dream-like visualizations, and I'm excited to see where this goes. If you're really excited by this research in multimodal neurons, I highly recommend checking out Yannick Kilcher's deeper dive into the paper, providing more information than this AI Weekly Update. Representation learning methods that combine image and text data is one of the most exciting areas of deep learning research right now, with the multimodal neurons things we just looked at, and CLIP, DALL-E, and other things like ImageBird and VisualBird and all these kind of things. So in addition to these new models, we also have a new open data set titled the Wikipedia-based image text data set, and we have 37.6 million entity-rich image text examples with 11.5 million unique images across 108 Wikipedia languages. So here's some stats about the data set compared to previous, the other kind of data you have available for image text learning. You have famously this MS COCO data set where you have like captions and things like that. In this case, you have 330,000 images, which is still a lot, but it's not as many as 11.5 million. And then you have 37.6 million text annotations to pair with those images. And I think MS COCO has so much variety because I think they have like 5 annotators each write a unique caption for an image or something like that. And then also is this column on languages. So none of these other data sets have as many different languages as are in this new data set. So they show some examples of how it's been annotated. They also have on the Wikipedia page, they show how the page title is a good pairing for this. The reference description with this half-dome image, and they also try to extract from the page description with the the title image on the wiki. So it's really exploiting the way that these Wikipedia pages are structured, because Wikipedia page is not like a randomly formatted web page for some concept. So they're able to extract labels by using this way of setting up the initial image that describes a concept on Wikipedia, and they describe some other ways of how they get other images out in this Wikipedia crawl data section of the paper. So then they also describe fitting some baseline models to it, how they have image text retrieval problem where you have the image input and then you're trying to find the most similar text input, so similar to the CLIP task of information retrieval. About a year ago on Machine Learning Street Talk, Tim Scarf, Yannick Kilcher, and I looked through Jan LeCun's 2020 ICLR keynote on these ideas of energy-based models and self-supervised learning, and overall we were a bit confused by the presentation, but this blog post has really brought a lot of these ideas together for me, and I think you'll really enjoy reading this as well. So the beginning of the blog post motivates this idea of self-supervised learning. Labeling data with supervised learning is a bit of a bottleneck. It's hard to really label this data, even though, personally I think that, if you look at data sets like COVID-QA or SciFact or, climate fever, these kinds of data sets with like expertise annotations from, say, biomedical researchers and doctors, I don't think that kind of supervised learning is going to be replaced by self-supervised learning anytime soon. But for general, understanding of having, particularly what it's describing is this idea of predictive learning. So as babies, we learn how the world works largely by observation. We form generalized predictive models about objects in the world by learning concepts such as object permanence and gravity. So you have this predictive model where you're always looking at this video data. It's something like, if you think about 1 year of life, 365 days, 24 hours in a day, blah, 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 all the way to 60 seconds in a minute, and then noting that a second of video data is usually 30 frames per second. So if you do 30 times 60 times 60 times 24 times 365, you see how many, if you're thinking about it like image data and video data for just 1 year of life, you'd see something like 95 million image frames. So that's one way I think that's kind of a funny way that I think about it. But this idea overall is that you have these predictive models where you're modeling your world, and it's not just image, data. Also, it's audio data, sensor data from your, touch and proprioception, how you're oriented in space, and all these different kinds of things. To get back on topic with the blog post, the idea is about how do we learn common sense? And the idea is that by doing this predictive modeling, that's how we learn common sense, and common sense is the dark matter of artificial intelligence. By always trying to predict the future, that's how we build our common sense of what's a likely continuation of our current state. So then the blog post quickly describes some of the latest advances of self-supervised learning, Word2Vec, BERT, all this stuff. And now we're looking at the computer vision advances like SEER, which is the latest paper from Facebook, which we'll talk about next in this weekly update. It's the latest attempt to scale this up with real world data and have 2 billion unlabeled images for the sake of doing self-supervised learning. So now let's get a little more into this idea of self-supervised learning is predictive learning. So this is the idea of something like an autoencoder. You take an input, which would be like this entire cube as if it was all green, and you would mask it out, and now you're trying to predict what's been masked out. And this is BERT, you predict masked out intermediate regions of this input, and then you could also, you can do different ways of cutting this. So this way you're cutting the height too, not just the like the X, Y, this is X, Y, Z, or something like that. So it's illustrating this concept of masking out the input and then predicting what's been masked out. So now let's talk about this really exciting, I really enjoyed this paragraph describing the difference between self-supervised learning for language, like language modeling with BERT, compared to vision, and why we can't do language modeling with pixels. So to begin, it's not like autoregressive language modeling in pixels and images is something that's never been tried before. OpenAI had released this famous paper, ImageGPT, where they're doing this autoregressive modeling of pixels by using something like a 7 billion parameter transformer. And it does perform pretty well at doing this task of having these image continuations of the doggy ball, the cat image, and then the elephant and this Go board. So it does a pretty good job, but it still doesn't have the same representation learning ability of these latest self-supervised algorithms like SimClear, MoCo, or SimSciM, these contrastive representation learning algorithms. So the question is, why is language modeling so successful for text data, but not image data? And this explains it really well. So the idea is that when you have uncertainty about how to predict the future, like the blank chases the blank in the savannah, the model doesn't know whether it should put density on lion or cheetah, because both of those are valid ways of filling out this text prompt. But when you have language data, you have something like 37,000 words in your vocabulary. So 37,000 is a reasonable amount of different predictions to have a probability distribution over all of these different potential outputs on the 37,000 candidates. So you can have this probability distribution over this set of words, whereas with respect to trying to finish pixels, it's not computationally feasible because there's so many different, it's known as continuous data because there's so many different ways of, it's like an infinite distance for predicting this continuation, having a probability density over all of the potential continuations of, say, image frames and video data is impossible. So that's the motivation for why we can't have these probability distribution models in predicting the future for pixels. And particularly what this is known as is an energy-based model. So an energy-based model is just going to compute a similarity score between X and Y. An energy-based model is going to return a score about how much X agrees with Y, rather than a probability distribution over all the other Ys that might be paired with X. So energy functions like this, computing a compatibility score between X and Y, is the unifying idea with contrastive learning. So when we have contrastive learning, we pass in two different augmented views of an image, and then we compute this energy function, which is the similarity of these two pairs. So this is known as a joint embedding architecture. We're learning how to embed two different things at once, and we also may go out of modalities, as we've seen previously, like the Wikipedia dataset of image-text pairs, or CLIP, and the resulting multimodal neuron thing where we look through this encoding layer. This is this idea of learning a joint embedding architecture so we can learn an energy score for these two different inputs. But the problem with this contrastive learning is that it's hard to find the negative pairs to show it how to shape the boundary and how to learn when to assign a high energy to incompatible points. So we've seen a lot of approaches in contrastive learning, particularly when they do the SEER experiments. They're going to use the suave clustering, where you'd push it away from, say, a centroid that represents like a clustering of embeddings from the other object categories. But we also might use, say, data augmentation views from other images in the batch, or all these other kind of strategies of trying to find where to learn to assign high energy or high dissimilarity between these two pairs. So it's challenging to train these contrastive models and find how to train it to put with the negative pairs. So the idea is that another way to solve this problem of predicting the future is with latent variable models like the Generative Adversarial Network Framework. So the Generative Adversarial Network Framework has this latent vector Z, and the latent vector Z helps with the decoding so that you can have uncertainty in predicting the future. So finally, the article concludes with some different ideas of how to bring these latent variable models to life. So overall, I thought this was a really interesting article bringing together this idea of energy-based models, joint embedding architectures, the differences between language and vision for self-supervised learning, and this exciting paradigm of latent variable models for modeling uncertainty and predicting the future for self-supervised learning in vision. So next up, we're going to look at the latest experiments from Facebook, this SEER system that's trained on billions of Instagram images. Facebook AI has published a new cutting-edge research on scaling up self-supervised learning. So the promise of self-supervised learning is that it can learn with unlabeled data. So this could be, say you have a self-driving car that drives around and collects a ton of different video and image data, or you're just collecting all the images from the internet. The core promise of this line of research is that it can learn from this massive amount of unlabeled data. So that's the core objective of SEER. SEER is scaling up the amount of data that's used to train these models, and you see the comparison between the original version of the paper, SimCLR v2, and then the Google's Vision Transformer for the sake of just putting another point on this to see where these algorithms are overall. So this is an improvement on the latest work on doing this self-supervised representation transfer. It's not a semi-supervised loop like in fixed match or co-match, and you're just doing self-supervised learning, and then you fine-tune that on ImageNet, and you can use only 1% of the ImageNet labels, and it will still be able to perform well using this representation. So in addition to scaling up the size of the experiment with a 1.3 billion parameter model and training on 1 billion random images with 512 GPUs, this work is also building on 2 other papers from Facebook. I've made videos on Henry AI Labs with both these papers if you're curious about it, which is the SWAV clustering algorithm. SWAV clustering, similar to other contrastive learning frameworks, you take an image, then you augment it twice, you encode it with your, the feature learning algorithm, and then you have this latent code Z, and in SWAV, you're going to form this codebook. So Z gets mapped to its nearest neighbor in the codebook, and then you're going to predict the codebook of the other pair with the other pair. So this one, XJ, predicts the code for ZI, and then XI predicts the code for ZJ. And so they also have this clever Sinkhorn-Knopp algorithm of doing this clustering in an efficient way. So I'm not sure exactly in the paper where it describes that, but it has this other algorithm of how they're going to cluster efficiently. And then this other paper, the RegNet architecture, is the product of designing network design spaces. This is a really exciting, really meta-level look at this AutoML neural architecture search problem, where not only are you searching through one of these neural architecture search spaces, but you're also parameterizing the search space itself. And so the search space is evolving, as is the performance on what's being discovered in the search space. So I thought this was a really interesting paper on this idea of how meta, how recursive can you get with this kind of idea of AutoML, and particularly taking AutoML not just at the level of learning rate, batch size, but really getting into designing these architectures by exhaustive search through what you can possibly put as a neural network architecture. So with that said, they're combining the RegNet Y architecture, scaling it up to 1.3 billion parameters. They're using 1 billion Instagram images. I'd also read somewhere they're using 2 billion images, so I'm not sure which one's correct. And then they use 512 GPUs trained with this SWAV clustering algorithm. So they describe some more about the details, these different background things, and they present the results. So this is comparing the results of SEER with these Instagram data source compared to, say, Google's JFT 300 million dataset used to train this vision transformer and get this result out. SWAV trained previously with a different architecture. So this is, I think, the ResNext architecture with a big X before the T, another design of the ResNets. I don't think it was a neural architecture search design. And this looks like another ResNet 152 with the width scaling thing. And SK, I imagine, is some kind of normalization layer. So this is comparing this performance with training on ImageNet data compared to Instagram data. And the key difference is that even though ImageNet has much less data, it's more curated than just randomly taking the 1 billion from Instagram. So if you're looking at this table, just looking at the comparison of million to billion, and then you see that the performance is about similar, it's worth noting that these billion images aren't so carefully curated. They're just like a random scrape compared to ImageNet, which has been manually annotated, so there probably isn't as much noise in the images. Or it's more, it also could be that ImageNet is more diversity in it. Diversity of the data would have an impact, I think, on this performance. So a few ways of interpreting it, based on what you know about this background. So then this is showing some performance with the few shot learning setting where you only have 1% or 10% of the labels to, transfer this representation into a new task. And this promise of, can we learn representations from a massive amount of unlabeled data that then lets us learn with less labeled data for downstream tasks? And that's a really exciting idea as well. So overall, I thought this was a really interesting paper, exciting results of scaling this up. So next up, let's quickly talk about how we're going to be using these self-supervised learning with our supervised learning data sets. So this paradigm is known as semi-supervised learning, where you have a combination of learning from unlabeled data and labeled data. And there's been a lot of frameworks that are trying to bridge exactly how we should do this loop together. So we've seen things like self-training with Noisy Student, where you pseudo-label the unlabeled data, then you scale it up, and that results in state-of-the-art ImageNet results using that JFT 300 million data set. We've seen things like FixMatch from Google as well, which has this consistency regularization with predicting the pseudo-labels on heavily augmented and weakly augmented image pairs. We have things like Salesforce has this co-match paper where you have this graph structure. So you kind of have like a graph embedding loss, and that's kind of an exciting idea. And so this latest paper, I didn't read too much about it. I just want to kind of highlight that this area of research is still active on trying to figure out these semi-supervised learning loops. It uses some idea of having a knowledge distillation is a common part of this idea of pseudo-labeling and predicting these pseudo-label distributions, and then also trying to match the output layer losses. So I thought this framework looks very similar to co-match in that they're trying to apply loss functions on the intermediate embeddings as well as the classification layer. It doesn't look like this has the graph structured loss of co-match, but it has a similar kind of idea of applying losses in the embeddings of the transfer between self-supervised representations to the supervised representations. And then it also has some supervision on the output layer itself. So it looks kind of like you're breaking apart the updates at the very last layer of the network as well as intermediate layers using knowledge distillation and representation consistency is what they call it. Next up, we're looking at this paper, Did Transformer Modifications Transfer Across Implementations and Applications? So this paper has a very similar feel to the paper Text-to-Text Transfer Transformer, the T5 model, also led by Colin Raffel. And this is another case of taking together all these different ideas. In T5, it was looking at things like the different pre-training objectives, also different architecture decisions, and different configurations of depth and hidden dimension width, and seeing what really results in better performance. And this is doing the same thing with recent advances to the transformer architecture. So the transformer architecture, obviously super popular, and people are trying to build on it constantly. We see things like designing new position embeddings, trying to design new normalization layers, getting away from layer normalization and trying other ideas, as well as things like replacing activations, compressing intermediate features, all these different kinds of ideas. Also, parameter sharing is a big one. So in section 3 of the modifications, they're going to list each of these things that they're going to ablate in this gigantic data table of testing all these different ideas out for superglue, extreme summarization, web questions, and machine translation. So we have different ideas like just probably the easiest modification is switching out the activation layer, trying out a new normalization scheme. This RE0 paper had been pretty interesting as a way of doing a new normalization and initialization to train transformers. The depth width trade-off. Embedding is another interesting idea where say you might not want to have as much dimensionality in your input embedding table as the output, or maybe you want to share weights for the two or so on, something like that. Parameter sharing, ideas like Albert, where you can just copy transformer blocks at say layer 4 and layer 8, redesigning the softmax, and then these big architecture transformations. I made videos on the Evolve transformer, which is used in the Mina chatbot, as well as the funnel transformer if you're interested in that. These are all ideas to do some kind of way of saving the computation of transformers. So here are the results of ablating all of these different modifications to the transformer in the same code base, in the same experimental setting. And you see that there aren't really any massive differences in any of these modifications. And so the authors describe some reasons for this in section 4. And probably the most interesting of which is how they describe that the importance of developing all these models in the same code books. I'm sorry, it's actually section 5 where they describe these different things. So they use this mesh TensorFlow code base. They don't say that that's probably the reason why they perform differently, but they do note that these things should be tested in the same kind of code environment, not overly tuning hyperparameters maybe is the problem with this. And then other ideas like that it might have performed well. Say the authors of Funnel Transformer were able to get a new result in superglue, but it just didn't transfer to web questions and so on. So they have these other conjectures about why this isn't really leading to massive improvements, but I definitely think it's interesting. Particularly, I thought it was interesting to see the evolved transformer because this is a product of neural architecture search. So I thought that this would be something that would perform, better because of the way that it was designed, but apparently not. So it's definitely a sobering look at these new extensions of the transformers, but it is worth noting that this isn't the same idea as, say, the long-range arena, a benchmark for efficient transformers. So it's hard to say. So with the transformers, these modifications build on the original encoder-decoder, and attention is all you need in that paper. So it's a different way of taking apart the transformer compared to papers like Transformer XL or the Linformer, Reformer. These are all ways of making it more efficient. So you get away from the quadratic complexity of attention, and you can attend over a longer input sequence. So rather than 512 tokens, imagine being able to take as input an entire book for doing something like question answering about that book. Obviously, you'd imagine that would be a better thing to do. So this benchmark is different from superglue web questions in that it's particularly trying to test these models on having long input sequences, and it's a very interesting data set as well. Long range arena, a benchmark for efficient transformers. So there's a couple of different ways of looking at the latest advances in transformer neural network architecture design. So next up, we have a new transformer design, perceiver, general perception with iterative attention. And it's worth noting that, compared to the last paper, to transformer modifications transfer, those transformer modifications are pretty subtle things relative to this perceiver thing. Ideas like vision transformer or, in my opinion, things like reformer are or transformer XL are a totally different idea. So this is a different kind of, it's not like a subtle transformer modification. This is a completely different architecture of using the transformer layers. So the idea behind perceiver is to try to make the transformer generalized to high dimensional input data. So particularly, we're trying to get transformers now to do image classification, maybe even predict video data, things like image GPT, audio data, all this kind of stuff. So this final model is going to directly attend to 50,000 pixels. So that's a lot different from the vision transformer that splits it into grids and then attends over these little grids. So this is going to be attending over this massive set of 50,000 pixels. So how does it do that? It does that with this idea of iterative attention. So the idea of iterative attention is that we have this latent array, which is our intermediate features of our neural network. This is n by d, which n by d is going to be a lot lower than n by c. And every now and then we're going to in intermediate layers of the model, we're going to project our original input into the key and value matrices. We're going to project our current feature space into the query matrix, and we're going to do the query key, softmax, and then multiply it by the value, and we're going to compress it and get a new feature space for our latent transformer representation. And then we're going to process that again for layer 2, 3, 4, 5. And then at layer 5, we're going to again attend to the original byte array. So then again at layer 5, the original high dimensional pixel grid gets mapped again to key and value matrices, query key, softmax, value, and so on. So this is the idea of iterative attention for adapting the transformer to the latest performance, and it surpasses performance on these other models and is successful, tested on a lot of different ideas. It's even tested on point cloud, which I thought was really interesting. So here's a performance comparison of a transformer that attends on 64 by 64 images compared to the perceiver, as well as a comparison with ResNet 50s and the vision transformer. So one of the most popular architectures for applying transformers to computer vision is this Google's vision transformer. And there's also a Keras code example implementation of this. I made a walkthrough video if you're interested in that as well, that will show you how to get started with this if you want to use it yourself. So the idea is you take an image and then you split it into these grids. These grids are treated as the sequence of tokens. You project them into a vector space, add them with a position embedding of the original position in the grid. So in this next paper, Transformer and Transformer, we're going to take apart this idea of this position embedding. So in the original transformer, they add this cosine function and sine functions to add the idea of left to right sequence ordering to the transformer. So if you're completely unfamiliar with transformers, it's important to note that this attention layer is a set operation, so it doesn't have any kind of original prior on, say, the local structure in images or on the left to right structure in text. So you add in this embedding to bias it to give it that information about position information. So this paper, Vision Transformer, is blindly writing 1 into the entire encoding of the top patch. So Transformer and Transformer is saying that that's too much of a simplification. You're losing too much of this local information by clustering the embedding of these patches together. So they have an inner block, which is the Transformer in Transformer block, where you're going to attend over within the block itself and then add those projection features back into the patch embedding. So the patch embedding now is a product of this particular encoding for the patch itself, and then as well as the global encoding. So you add these two things together, and then that's what goes into the patch for the TNT block. And surprisingly, this modification, which seems kind of like a very subtle thing to change, actually does seem to improve performance. Whereas at the bottom you see the direct comparison between vision transformers and the Facebook data efficient image transformer, and you see these gains. And particularly what we're looking at is it has less parameters, it's more computationally efficient, and it's performing better on top 1% accuracy. So it looks like having this local attention within this patch to even just add it back to the embedding really does improve the performance of this model, which is pretty interesting to see something like that happen. This next paper has the best title in the crop, Generative Adversarial Transformers. So what's missing from the StyleGAN architecture? Obviously attention and transformers. So the idea is that in the StyleGAN, you have this mapping from a latent vector z. This is the random latent variable that's added into the generator as it produces an image, and you first pass it through this mapping network where you have 8 fully connected layers, and then you have this W space, and the W controls the intermediate features using adaptive instance normalization. So the gain and bias parameters of adaptive instance normalization is controlled by this latent vector, and that's how it influences the generating of the network in the normalization layers. And they also have this spatially adaptive normalization where it's further going to be going along each of the different height width indexes as you go left to right and then top to bottom, and then computing the the normalization parameters across that channel dimension for each of those individual positions in the height by width grid of the height by width by number of features volume in these intermediate layers. So the idea of the GANsformer is to have an attention on these intermediate on this mapping network. So the attention can be used, they ablate a couple ways of doing this. They have this idea of top down where it's only the latents going to the image features, so an attention layer that goes from this into this, and then also having an attention layer from this back to this. So this signal will go back into the mapping network as well, which is kind of an interesting idea and not something that I'm exactly sure how the gradients are going to flow between, but it's this idea of adding self-attention between the latents and then the image features, and particularly using this attention operation rather than normalization layers or multi-layer perceptron mappings. This is a diagram of these ideas of top down, bottom up, attention between latents and then intermediate image features. And then they go on to show you some examples of their generated images, which look really great. The LSUN bedrooms, this clever data set for reasoning challenges, and showing how well this can model this kind of concept. And I think they show the clever benchmark particularly to show this idea of compositional reasoning in generative models. It's really exciting to see such a, these are obviously high resolution images, and it's able to produce them really well. And I think there is a subtle difference between just generating bedroom images compared to these clever images. So if you're curious about the state of the art in image generative models, this is a really great blog post that summarizes some of these latest advances, describing the vector quantized variational autoencoder, some of the subtleties to the StyleGAN 2 model, and then diffusion models, which I personally know nothing about. So this is describing some potential future trends, the idea of, we have models like VAE GAN, where you combine the prior on the encoding space with the discriminator loss and things like that, and there may be other ideas of combining GANs and VAEs and these ideas. What's going to happen as we scale this up? And then it has a description of each of these, the latest papers using each of these frameworks, VAE, variational autoencoder, GAN, and diffusion models. So I really enjoyed this blog post. It has a great overview of each of these models, and I highly recommend checking it out if you're curious about the latest advances in this vector quantized variational autoencoder stuff, which I think the next paper that we're going to look through, the predicting video with VQ-VAE, really explains it well. But here's another paper, blog post that collects a bunch of these papers that use and explain this framework. So next up is what I think is the most creative combination of ideas in this paper. I mean, doing self-attention on the StyleGAN architecture, that's really exciting too, but this idea of combining lottery tickets with aggressive data augmentation to solve the problem of learning from limited labeled data, I thought was really interesting. So the lottery ticket hypothesis, the idea is that within a dense neural network architecture, you can find a sparse subnetwork that will perform as well as the network trained from scratch. And that trained from scratch part is really important because we already know about this thing called pruning, where you can train a deep neural network and then you prune out most of the weights that are near zero and it'll still perform as well. But the key idea is that you can prune it from scratch and then it will train the sparse network from scratch. So this connection is saying that as you train that sparse subnetwork, it actually learns more efficiently. I mean, obviously it learns more efficiently because there's less gradients going through less weights, but it's also able to somehow perform better with respect to this data augmentation thing. Data augmentation is one of the most powerful tools that we have to learn from limited labeled data. And this is done by applying these transformations in the data space by, say, transforming, rotating images or translating them or affecting the color space. And this has been used previously in the training of generative adversarial networks. So this is a paper from NVIDIA. I've made a deeper dive video into it if you're interested, where they show a strategy for building on previous work to apply data augmentation to the real data set and what's produced by the generator as it goes into the discriminator, and then building on this idea to use data augmentation to learn generative adversarial networks from, say you only have a data set of 1,000 labeled examples, something like that, obviously. So this is the first work on using data augmentation. And so now in this paper, Ultra Data Efficient GAN Training, we're combining data augmentation not only in the in the input space, but also in the latent space. So this idea of latent space augmentation is that any deep neural network architecture, it takes in as input these high dimensional images, which we'd apply, say, rotation translation to, and then it maps it into these feature vectors. So we can add this delta, which is this noise, to these intermediate features as a form of feature space augmentation. So in this case particularly, it's using the adversarial augmentation controller from Google Research. And basically, so you're saying how exactly should we augment these features? And one strategy would be to use an adversarial controller that's just trying to add noise such that it corrupts the performance of the model, rather than some other strategy. There's a recent paper called Modals and ICLR. I've made a video on that paper really recently that shows other ideas other than using an adversarial controller for designing these feature space augmentations. So overall, this is the combination of the algorithm. You iteratively keep looking for these lottery tickets, and then you train the lottery tickets with aggressive data augmentation. And that combination of those two things, which maybe don't sound like they go together so much, results in better performance. So building on this baseline, interesting chart of showing this inception distance score, which is a metric of generated image quality. Maybe we'll find another table of this. So this is comparing the big GAN with less parameters, less training data, to this new combination of lottery ticket pruning and adversarial augmentation. So definitely a really interesting paper and a really exciting research direction on training generative models with less data. As exciting as generative adversarial networks are, the star of the show recently has been the vector quantized variational autoencoder. So the high-level idea of the vector quantized variational autoencoder is that in an autoencoder, you have this bottleneck where you first take a high-dimensional input like an image and you map it into a latent vector Z. So it goes from image into latent vector Z in the encoder, and then from Z back into an image space output for the decoder. So that's how you do an autoencoder of just any image, you compress it, and then you reconstruct it. So the idea now and then variational inference has this idea of assigning this prior over the latent vector Z. So what kind of distribution should these latent vectors Z have? So say the latent space isn't just all clustered, or it could have all sorts of things, like where it could map each image to a super specific coordinate point in that Z vector space so that it can reconstruct it, but it has no real semantics with the space. And ideas like that is why they enforce these priors over the distribution of these latent vector Z's. But aside from that, the key idea here is that with these latent vector Z's, they're going to get mapped to a discrete codebook. So from this latent vector Z, it then gets mapped to its nearest neighbor in the codebook, similar to the original discussion in the weekly update where we had the suave clustering algorithm. The suave clustering algorithm is going to map that latent vector Z for contrastive learning to its nearest neighbor in a discrete codebook that's formed by clustering all the embeddings. So similarly to that, the vector quantized variational autoencoder has a learned codebook, and it's learned by doing this thing called the straight-through estimator. And this is a great paper that explains it a bit and describing this idea of how do you put gradients back through these discrete operations. So it has this structure of learning this codebook. And then one other idea is that the codebook is hierarchically organized. So I'm not exactly sure how that is represented in the gradients and that kind of idea, but the idea is that you have this high-level representation that would, say, generate like a scene, and then you'd have other variables in the discrete vector that code for subtle changes like high-frequency patterns. The objective of this paper is to model video data using the vector quantized variational autoencoder. So you're using these large-scale data sets like Kinetic 600, and you have high-resolution image frames of 256 by 256. So the idea is that in order to break apart this problem of trying to do sequential modeling of high-resolution images, you're going to first compress the frames into the discrete codes from the vector quantized variational autoencoder, and then you're going to use an autoregressive model to predict in this latent space. So you're modeling in the latent space to predict the future frames, and then you can render the generated latent codes by using the decoder half of the variational autoencoder from the output of the autoregressive model. So since this is video data, it's best to look at the web page, not the paper for to get a sense of the results. So here are some examples of videos that have been generated. We have this original conditioning frame that seeds the model, and then it predicts this continuation of the waves. And then this is another example where we have traffic, and it's predicting what's going to happen as a car is driving by. This might be like a self-driving car kind of data set as it looks to the left as you drive through a street. More examples of these. So I think this is a really exciting work. It looks like it's really generating it. It's definitely exciting to see video data, even though this whole deep fakes thing is something that's kind of a bit of a crazy application of this stuff. So I think it's useful to have a sense of how this is advancing, and it looks like video data, 256 by 256 is pretty high resolution, Kinetic 600, pretty high diversity data set. So I definitely think this idea of predicting video is something to keep an eye on. So also, if you're curious about it, this is the original paper that proposes the vector quantized variational autoencoder. And this is something that I'm trying to learn more and study more about myself. And it seems like it's a really powerful architecture for doing generative modeling. Next up, we have data augmentation for object detection via differentiable neural rendering. So I think this started with this paper, Neural Radiance Fields, or at least that's when I became familiar with this. This is a way of taking a two-dimensional image and constructing a three-dimensional representation of it so that you can do these rotations. So you have this picture of this park bench, and you see how it can rotate it in a novel way compared to what we've been using for data augmentation, where we just like rotate it on the y-axis. So here are some more examples. Facebook has published this blog post where, say you took a picture of a dog and you can rotate the dog image. So here's another example of what this is capable of doing. So the way that they apply data augmentation for object detection with differentiable neural rendering looks to be what they do is they have the bounding box, and I think they're going to rotate everything else around the ground truth annotation. So you have this training data set where you've labeled this bounding box, and I think they're going to rotate the scene around it, is how I'm understanding this. So they're going to convert this into a point cloud representation where you have this three-dimensional space, and then you can slide this differentiable renderer where it's this camera that takes like a two-dimensional projection of the three-dimensional space and then produces this new augmented example by rotating around the bounding box there. I'm not sure if that's exactly correct, but that's how I've understood it from quickly kind of skimming this paper. So they present some of the results on doing this and the different details of doing this. So again, these are some visualizations of the annotations. Probably best to have like a video, but I wasn't able to find the project page. But so here are some of the results, and I think it's an interesting direction. I didn't really completely read the details of this, so I'm not exactly sure what's happening, but I do think this concept of augmenting data by having these rotations should lead to interesting results. One of the most important problems to solve or get a better understanding of is the distribution shift problem for when we take a deep learning model and then deploy it into the real world. The problem is that the distribution of the training set isn't always the same as the distribution of the test set. And this dataset paper, Wilds, that came out about 2 months ago, has a collection of these different instances that describes exactly what happens as distribution shift happens in the real world, and describes these ideas of domain generalization, subpopulation shift, and it provides examples like, let's describe the satellite one really quick to get the idea. So the idea of the satellite distribution shift is that you train it on data from 2002, 2009, 2012, and then you shift it to predicting 2016, 2017, where the the buildings, they build new buildings, and the distribution shifts in that way because over time the satellite images are going to be changing as new things are built in the city, and that kind of idea of labeling things can shift over time. So this is kind of the idea of the historical data split. So I really enjoyed this presentation on principles for tackling distribution shift, beginning by describing the problem, then presenting 3 paradigms for solving it: pessimism, adaptation, and anticipation. So in this slide, it shows you the beginning, this idea of offline reinforcement learning, how the distribution shifts with the policy that's being optimized, collects different experience from the historical data, the shift over time, this idea of predicting correlations between search engine queries and flu epidemics up to 2009, and then by the time it predicts into the future, once it gets to 2013, the model's completely fallen apart. Same idea with language modeling, and then describing some more instances of the Wilds data set and toxic comments, molecular property prediction, and then describing in detail these 3 paradigms of pessimism, adaptation, and anticipation. So pessimism, to give a high-level overview of these 3 ideas, pessimism is where you're particularly training on the hardest examples. It reminds me of, say, like boosting in the ensemble learning sense, where you're trying to explicitly resample the hardest examples. Or maybe there's another paper that is titled something like Training Neural Networks by Focusing on the Biggest Losers, where you're particularly trying to find these hard sets. And you also will kind of parameterize the data splits itself. So you have like a space of the data domains itself and maybe metadata about the data domains as well. So I recommend watching the talk for getting more information about that. Adaptation is this idea of, say, model agnostic meta-learning, learning these parameters that can quickly shift to a new distribution. That's an interesting idea as well. Then anticipation is where you have this latent variable that can do this dynamics modeling and maybe get ahead of distribution shift and have a plan for distribution shift by modeling it with latent variable architecture. So some pretty ambitious ideas, and there's a lot to this, and is one of the cutting edge research areas. So I highly recommend watching this talk to learn more about it than what I've just given you. Also new this week is the release of automated machine learning AutoML for genomics. And I think this is really interesting. I don't have too much to say about this because I don't know anything about genomics data, but I do think it would be exciting to see, this integration and getting these problems into a setup where, say with these Kaggle competitions, how we easily understand what the input outputs are for machine learning. And I think this is bringing this closer to bringing together machine learning scientists and genetics researchers who really know what this kind of stuff means. So here's the GenoML kind of package. So they have these different ways of processing input data, data munging, harmonization, model training. So, again, I don't know too much about this, but it does seem like an exciting project. Thanks for watching this recap of the latest advances in deep learning and artificial intelligence this week. Please subscribe for more updates and more content about deep learning and AI.